December 19th, 1944. Across 3 battlefronts spanning some 6 million square miles, American machine gunners filed 47,000 after-action reports. The figures inside those reports would overturn 6 decades of military engineering orthodoxy. Under real combat conditions, gas-operated machine guns, the accepted, supposedly superior design, logged a 34% stoppage rate. Browning's recoil-operated designs recorded only 3.2%. Identical ammunition, identical soldiers, identical war. One decisive difference. When John Moses Browning first presented his prototype to the U.S. Ordnance Department in 1900, the assembled experts believed they knew precisely what he had done wrong. He had created a machine gun that allowed the barrel to move rearward with each shot, using recoil itself to drive the action. Mechanically unsound, they argued, because a moving barrel introduced alignment problems, accelerated wear, and degraded accuracy. Gas operation, they said, was the established standard. They dismissed Browning. For 40 years they dismissed him, until the frozen tundra of Alaska, the choking humidity of the Pacific Islands, and the thin air at 25,000 feet over Europe demonstrated what the experts had failed to predict. Simplicity proved deadly effective. The prevailing wisdom in 1900 carried an elegant certainty. Automatic weapons should tap off propellant gases to run their mechanisms. Hiram Maxim had established the principle in 1884, with a gas-tap design adopted by the British. By the century's turn, every major military power agreed. Channel some of the cartridge's explosive energy through a gas tube to a piston. Let that piston cycle the bolt to extract and chamber rounds. The approach was mechanically sophisticated, theoretically sound, and battle-tested in earlier wars. So when Browning walked into the Ordnance Office with a design that violated these conventions, skepticism was natural. Browning's argument was almost naively straightforward. Allow the barrel to recoil, use that rearward motion to unlock the bolt, eject the spent case, and operate the firing mechanism. Then a heavy spring would push the barrel forward, strip the next round from the belt, slam it into battery, lock, and fire. The whole cycle completed in 1/10 of a second. No gas tube, no piston, no adjustment screws, only barrel, bolt, and spring. 3 major assemblies, doing what the firearms forces already tended to do when it fired. Procurement records captured the Ordnance Officer's verdict with bureaucratic exactness. Mechanically unsound, a moving barrel would create alignment issues between barrel and receiver, increase wear on locking surfaces, and limit accuracy. Gas operation was the modern, efficient philosophy. Recoil systems required excessive mass to absorb stress, and that weight made them impractical for a mobile modern army. Those technical objections were defensible on paper. A moving barrel meant more mass in motion, heavier parts to withstand stress, and looser tolerances that ostensibly undermined precision. It also meant rejecting decades of European precedent asserting that harvesting gas was the state of the Entente. What the procurement analyses did not acknowledge was what Browning had learned over 2 decades of tinkering in his Utah shop. Gas-operated guns demanded extra parts that recoil systems entirely eliminated. A gas tube to siphon pressure, a piston to convert that pressure into motion, regulators to tune the system for different ammunition or environments, and seals to keep fouling at bay. Each added component was a potential failure point, a place for fouling to collect, corrosion to begin, or impact damage to disable the weapon. Browning's recoil method instead relied on mass and momentum, mechanical judo that redirected existing forces, rather than inventing new ones. At Browning's death in 1926, the firearms community's response was telling. Obituaries lauded his lever-action rifles and pump shotguns, while treating his fixation on recoil-operated automatics as an interesting sideline rather than his defining contribution. The British remained loyal to refinements of Maxim's gas system. The Germans developed the MG-34, a recoil design, but one of extreme mechanical complexity. Some 150 parts were required for it to function. The United States, by contrast, hedged its bets and maintained production lines for both approaches. For both gas and recoil systems, the U.S. military maintained production without fully committing to either doctrine. By 1941, American factories were turning out 4 different automatic weapon types in massive quantities. The 30 caliber M1919 Browning, costing $667 apiece, used 42 components. The water-cooled M1917 Browning, at 2,165 per unit, used 45. The 50 caliber M2 Browning's scaled-up recoil design for vehicles and aircraft, ran about $2,100, assembled from 44 parts. Its competitor, the Browning automatic rifle, BR, relied on gas operation to save weight and cost, just $319. But needed 87 components to function. No one yet knew which philosophy would prevail where it counted most, in the filth and fury of battle. Procurement officials kept arguing in Washington offices and ordnance test grounds, exchanging theoretical advantages like artillery salvos. Gas operation promised lighter weight and softer recoil. Recoil operation offered rugged simplicity with fewer precision parts. Gas systems could be fine-tuned for ammunition variations, while recoil systems needed no tuning at all. Each faction could cite European experience, metallurgy, and ballistic tests backing its side. What neither possessed was large-scale, real-world reliability data under combat stress. That changed on December 7, 1941. When Japanese bombers hit Pearl Harbor, theoretical elegance lost all relevance. Within 3 days, American troops from the Aleutians to the Philippines were fighting with whatever weapons logistics had issued them. Some carried gas-operated bars. Others bore recoil-driven Brownings. None of them cared about design philosophy. They cared only about one thing: which gun would keep firing when everything else collapsed. Thus began the largest unplanned experiment in automatic weapons reliability ever recorded. Across 6 million square miles of battleground, Arctic tundra, Pacific jungles, North African deserts, European fields, U.S. soldiers became unwilling participants in a live trial. The question was simple: which principle worked better in the worst conditions? Gas systems, with their intricate energy tapping, or recoil systems using raw momentum? The answer would emerge from stoppage rates, maintenance records, and after-action reports written by men whose lives depended on dependable firepower. Physics began to silence theory on Attu Island in May 1943. This westernmost Alaskan outpost sat buried in fog so thick visibility rarely exceeded 100 feet. Temperatures hovered near 28 degrees Celsius, winds reached 45 mph, and Japanese troops held the heights above tundra that swallowed boots and drained strength from every uphill assault. American infantrymen, many from warm southern states, carried 3 automatics into the freezing chaos: M1 Garands at 9.5 pounds, Bars at 19.4, and M1919 Brownings at 31. Within 3 days, nature delivered its verdict. The temperature dropped to 19 degrees Celsius overnight. Fog still clung to the slopes as assault teams prepared their attack. Of 214 bars issued for their portability and firepower, 89 stopped working entirely by 1100 hours. The cause wasn't surface ice. Troops could clear frost from external parts easily. The failure lay hidden in the gas system, where moisture from the gunner's breath and the weapon's heat cycles froze solid inside the narrow gas tube, the very artery that powered the mechanism. The science was merciless. Gas guns bled off pressure through a small port in the barrel, sending it down a tube barely 0.177 inches wide to drive a piston. That delicate passage, ideal in temperate climates, became a perfect ice trap in sub-freezing air. Any condensation inside, and there was always some, could freeze across that tiny opening. Even partial blockage cut gas flow, causing short stroking, where the bolt failed to travel far enough back to eject a case or chamber. Around, The rifle became a single-shot weapon, manually cycled if the piston hadn't seized completely, thawing. A frozen bar took 15 minutes over a field. Stove, then careful reassembly. With gloves thin enough for dexterity, but thick. Enough to avoid frostbite. 15 minutes in combat was forever. Squad leaders watched in frustration as their automatic firepower vanished just as Japanese counterattacks emerged through the fog. With bars frozen solid, soldiers fell back on their M1 Garands, or cold steel, and fought on. They kept climbing, using whatever still functioned. The M1919. Brownings kept roaring. Maintenance reports from the Attu. Campaign listed 41 stoppages across 2,847 recoil-operated guns, a failure rate so low that ordnance officers initially suspected the figures were incomplete. The explanation showed precisely why Browning's seemingly crude mechanism triumphed where the more refined gas system froze. Recoil operation produced a violent, full-stroke motion every time it fired. The barrel slammed backward against a massive spring. The bolt flew open and flung empty cases 15 feet away, and the return spring hurled the assembly forward again to feed and fire the next round. That sheer mechanical violence made ice formation impossible. Any moisture that entered the Browning's internals was expelled by the next shot's recoil energy. The weapon's heavy mass and brutal springs generated kinetic force in the hundreds of foot-pounds, enough to crush or fling away any frost that tried to cling to moving. And parts gas operation depended on siphoning a sliver of pressure through delicate channels. Recoil operation turned the entire gun into a hammer that bludgeoned dirt and ice into submission. It was the difference between threading a frozen needle and driving a nail through a block of ice. Sergeant Thomas Doyle of the 7th Infantry Division had grown up on a Wisconsin farm where his father taught him that any tool that froze could kill a man in winter. He kept meticulous logs from training onward, knowing that metal in deep cold obeyed its own set of rules. His M1919, which he called Bertha with a farmer's practical affection, developed quirks he charted carefully. She liked a slightly looser headspace when the mercury dropped below freezing. The cold shrank the steel enough to tighten tolerances. She needed heavier oil on the buffer spring because normal lubricants turned to wax in the chill. Most of all, she ran best almost dry, while bar gunners, following regulations, drowned their weapons in oil that congealed solid. The Browning's savage recoil didn't depend on frictionless contact the way a gas piston did. By late May, when the battle for Attu ended, casualty lists included figures that had nothing to do with bullets. 89 soldiers had fought uphill with semi-automatics after their bars froze, facing Japanese machine guns that never stopped because the defenders didn't have to advance through open tundra. The after-action summaries captured the point with bureaucratic restraint. Bar reliability in Arctic conditions insufficient for sustained automatic fire support. Request immediate reissue of M1919 to all assault elements. Within 2 weeks, every frontline unit under Alaska Command carried recoil-operated Brownings, while gas-operated bars were sent to reserve forces in milder regions. Doyle wrote home that June in the plain speech of a man who had seen theory freeze to death. The Browning's ugly, heavy as sin, loud enough to make you deaf. But when your bar's iced solid and the Japanese come through the fog, that ugly 30 is the prettiest thing you ever saw. His detailed logs, temperature readings, malfunction types, comparative notes reached Washington by July. The Ordnance Department's reply came with trademark caution. Isolated occurrence. Arctic environment not representative of standard operating conditions. But Browning's proving ground was only expanding. The same recoil system that survived the subarctic was now fighting in every climate where U.S. troops deployed. The next trials would unfold under heat and salt instead of snow. The Pacific's humidity, blazing temperatures, and corrosive sea air waited to deliver their verdict on whether simplicity or sophistication endured under pressure. The Pacific War quickly showed that moisture could be as lethal to weapons as cold. Island campaigns from Guadalcanal to Luzon turned mechanical refinement into a liability. Temperatures ran from 90 to 105 degrees, humidity from 85 to 95%. Salty air carried microscopic corrosion that crept into every joint and seam. Marine armorers found that even well-cleaned and oiled bars began developing rust pits inside their receivers within 48 hours of island exposure. Gas-operated systems, with their tight tolerances, narrow tubes, and precision pistons, became breeding grounds for oxidation. On New Georgia in July 1943, a natural field experiment formed that would transform U.S. weapons policy. The 43rd Infantry Division came ashore with 412 M19-919 Brownings, 289 bars, and 156 M1 Garands. All fired the same .30 caliber ammunition, endured the same weather, and were maintained by soldiers trained the same way. After 12 days of near-constant fighting in 94-degree heat and endless tropical rain, the operational data spoke louder than any theory Washington could cling to. Of 412 recoil-operated Brownings, 397 were still fully serviceable, a 96.4% function rate. Only 15 had been pulled for parts replacement, a number so small it forced the engineers back home to rethink everything they thought they knew about modern design. Most of the M19-19's few mechanical issues came from worn buffer springs and cracked feed poles caused by relentless use. Out of 289 bars, only 177 were still running, a 61.2% rate. 112 were out of action, 78 of them specifically for gas system corrosion that clogged or constricted the narrow channel between barrel and piston. Of the 156 M1 Garands, 140 kept firing, an 89.7% success rate, with 30 sidelined for pitted gas cylinders that caused short stroking. The physics behind these numbers made clear why Browning's supposedly crude design reigned supreme in the tropics. The gas tubes in bars and Garands were only about 1/16 of an inch wide, so narrow that a pinpoint of rust could choke off nearly half the flow. Every round sent hot gas, moisture, and carbon fouling into those tiny pipes. In air saturated with humidity, that residue absorbed water and built corrosive salts overnight. Even meticulous cleaning couldn't stop microscopic pitting that gradually narrowed the tube until cycling failed. The M1919's recoil-driven mechanism, by contrast, used huge, overbuilt parts meant to be brutalized. Its bolt weighed nearly 2 pounds, its driving spring compressed with 90 pounds of force. Those oversized components were indifferent to surface rust or light corrosion. The bolt's momentum and the spring's violence simply smashed through friction that would paralyze a gas piston. Gas systems demanded cleanliness to function. Recoil systems functioned because they didn't need it. Corporal James McWills of the 164th Infantry, once a North Dakota bank clerk, brought the same obsessive precision to the jungle that he'd once applied to balance sheets. His waterproof notebook became a treasure trove for post-war reliability studies. Every jam, every cleaning, every broken part was documented in tidy script. The entry, dated August 15, 1943, read like a lab report. Bar number 7738, gas plug removed. Found green corrosion obstructing 70% of tube. Cleared with rod. Functioned 47 rounds before recurrence. Replaced with M1919 number 42891. Fired 2,400 rounds over 4 days. 0 stoppages. Exterior rust heavy. Action normal. McWills had learned at Guadalcanal that dependable guns decided who lived. His squad was wiped out during the first week, everyone but him and the M1919 gunner. From then on, he treated weapon data as sacred record-keeping. Over 18 months, he tracked 47 weapons across the New Georgia and Philippine campaigns, noting patterns invisible to individual users. Brooding 1919 stoppages traced mainly to ammunition defects, weak powder charges, corroded belts, damaged cases, or bad extraction. Bar stoppages traced to the guns themselves, gas fouling, spring fatigue, extractors snapping under stress when trying to overcome insufficient gas pressure. The data revealed what procurement theory had overlooked all along. Gas operation traded complexity for paper advantages that evaporated in the field. A 19-pound bar offered no advantage over a 31-pound M1919 if the lighter gun spent 60% of combat time awaiting repair. Reduced recoil meant little when the weapon failed to cycle, and the elegant concept of harvesting gas from the barrel became its own downfall once tropical humidity turned every gas passage into a rust factory. By October 1943, the Marine Corps Gazette broke the bureaucratic silence with an article titled "Automatic Weapons Reliability Under Tropical Conditions." It was the first official acknowledgement that recoil systems had proven superior when tested under real war conditions. The conclusion was cautious but unmistakable. Comparative field data indicate that recoil-operated crew-served weapons demonstrate significantly higher operational readiness than gas-operated types in high-humidity environments. Recommendation: prioritize recoil-operated machine guns for Pacific theater use, Army Ordnance replied with its usual quiet maneuvering. No press releases, just procurement changes. Rifle programs would continue using gas operation for individual soldiers, whose weapons could be cleaned and serviced between fights. But for crew-served guns, where reliability defined survival and constant fire support, decided victory, Browning's once-rejected recoil principle became official doctrine. The shift unfolded not through grand declarations, but through production orders and requisition logs. Yet from that moment forward, every machine gun issued to American troops carried John Browning's vindication in steel and recoil. Every combat unit across the Pacific began to notice their arsenals shifting toward the guns that never quit. The M2 Browning represented John Browning's recoil principle pushed to its ultimate scale. Chambered in .50 caliber and weighing 84 pounds without ammunition or mount, it was recoil operation magnified for aircraft and vehicles. It hurled half-inch rounds at 450-550 per minute, with an effective reach beyond 2,000 yards. By mid-1944, the 8th Air Force was dispatching 1,000 bomber formations over Germany, and each B-17 Flying Fortress carried 13 M2 Brownings, mounted in waist, tail, ball, and nose turrets. That meant roughly 7,800 rounds of .50 caliber ammunition per plane, and 13 separate firing stations that all had to perform flawlessly at 25,000 feet, where oxygen was scarce and the temperature plunged to 40 below zero. Luftwaffe debriefings soon revealed something unexpected. German pilots reported that American defensive gunners could maintain fire longer than their own crews under similar conditions. The finding baffled German analysts. Training levels were comparable, ammunition quality roughly equal. The difference was mechanical, not human. German bombers relied on MG-131s chambered in 13mm, recoil-operated like the Browning, and MG-151 cannons in 20mm, which used gas operation to handle their higher power output. The MG-151s delivered tremendous firepower when they functioned, but Luftwaffe armory records showed stoppage rates of 8 to 12% during extended bursts, caused by gas system overheating at altitude. Between January and June 1944, American B-17 gunners submitted 23,000 combat reports. The M2's stoppage rate across those engagements was 2.1%. The technical explanation again pointed to Browning's genius. His gun used its own violence to stay clean. Each shot produced such forceful recoil, about 3/4 of an inch of rearward barrel travel, that carbon deposits were literally shaken loose before they could accumulate. The M2 could fire 200-round bursts without cleaning, something no gas-operated weapon could manage. Their narrow passages simply clogged with soot long before reaching that threshold. Technical Sergeant Robert Harper of the 91st Bomb Group, The son of a Lutheran minister from Iowa treated his B-17 waist guns with almost religious devotion. Between missions, he disassembled, cleaned and studied each component of his twin M2s, convinced that mechanical discipline was a moral obligation to his crew. His firing station became an unofficial classroom where replacement gunners learned that faithful maintenance meant survival. Harper's particular gift was mechanical intuition under fire. He could recognize malfunctions by sound and vibration, even through his oxygen mask and thick sheepskin gloves, hands numb from cold. Over 94 missions, his M2s never once failed. 3 separate fighter assaults were survived because Harper diagnosed issues in seconds. Bad ammunition, twisted feed chutes, debris in the belts, while other gunners' stations went silent. He'd seen bombers fall out of formation when their guns jammed at critical moments, and concluded that survival often depended less on courage than on whether a man truly understood his machine. The M2's design made that understanding possible. 44 parts in total, barrel, bolt, spring and feed assembly, each one learnable by touch. Gas-operated guns, by contrast, hid their complexity behind fragile systems few could master under combat stress. Yet Harper wrestled with spiritual unease between missions. He questioned whether praying for his weapon to keep killing was reconcilable with his faith. During the long, freezing hours over Europe, he found peace in a single conviction: protecting his crew was his calling. Keeping his M2 alive was how he served both God and the 9 men who depended on its thunder. That belief steadied his hands through endless raids, through the red-hot barrels and the smoke that scorched his gloves. The M2 endured every mission's abuse, because recoil didn't falter under heat the way gas systems did. By early 1945, the air war in Europe was effectively over. B-17 formations grew so massive that Luftwaffe attacks became rare. On the ground, however, a new challenge arose. Critics pointed to German MG-42s as proof that Browning's designs were outdated. The MG-42's blistering silent 200 round per minute rate of fire far exceeded the M1919's 400-500. Achieved through an intricate gas-driven mechanism of more than 150 parts. The M1919, with its 42-part simplicity and recoil-powered reliability, fired slower, but it always fired. The barrel was swapped twice after prolonged firing missions wore the rifling smooth. The buffer spring was replaced once when compression fatigue slowed the cycling rate. The extractor was replaced 3 times after breaking from sustained use. Yet the bolt, barrel extension and receiver, the heart of Browning's recoil system, never needed replacement. Jacobs brought the weapon home to Chicago and kept it in his garage as a tangible reminder of the 11 months that had kept him and his squad alive between 1941 and 1945. U.S. factories produced 2.08 million M1919 Brownings and 400,000 M2 Brownings, 2.48 million recoil-operated machine guns in total. Those arms fired an estimated 12.8 billion rounds across every theater where American forces fought. The recorded stoppage rate across platforms, environments and users was 3.2%. No rival design, American, British, German or Soviet, matched that figure. Those numbers were more than an engineering victory. They were the difference between life and death for soldiers issued weapons that functioned when everything else failed. The M2 Browning that John Moses Browning conceived in 1921, once written off by procurement in favor of gas systems, remained in U.S. service for the next century. Some M2s built in 1933 still served in Pacific Shore batteries at war's end, each having fired over 200,000 rounds without catastrophic failure. Between 1900 and 1945, gas operation yielded 19 major military designs adopted worldwide. Browning's recoil principle produced 6. By 2000, every gas-operated system from that era had been retired. The M2 endured. Browning died in 1926, convinced institutional inertia would never fully accept his recoil concept. He spent decades watching procurement panels favor European precedent and sophisticated gas mechanisms over his mechanically simple solution. He did not live to see combat data from 3 continents prove that his once dismissed idea, harnessing recoil rather than fighting it, produced the most reliable automatic weapons in military history. The genius lay not in complexity but in clarity. Every gun generates violent recoil, a force engineers typically tried to damp or divert. Browning asked, what if that force powered the weapon itself? What sounded mechanically unsound in 1900 became the bedrock of American automatic weapons practice for a century. The simplest mechanism, driven by nothing more than Newton's third law, outlasted its competitors because it excelled at one task. It kept firing when everything else stopped.